it's my great pleasure to introduce the speaker today, okay, Professor Sinya Aoki from Yukawa Institute for Theoretical Physics at Kyoto University. Yeah, Professor Aoki received his PhD in 1987 from University of Tokyo, okay, and then he went to Brookhaven as research associate from 1987 to 89, and then he moved to State University of New York as Stony Brook, and stayed there until 1991. Is it? 91, okay. 91 for 2 years, and then returned to University of Chicago as assistant professor. And then he stayed there and until just recently, okay, yeah. And he was promoted to full professor in 2001, right? 2001 at Chicago. Okay. And recently he moved to Kyoto, okay, at the Yukawa Institute for Theoretical Physics. Okay. Yeah, Sinya is well known for his many theoretical and numerical work in lattice QCD and nuclear physics. Okay. Yeah. So I would regard Sinya as one of the great thinker, okay, in lattice QCD. Okay. Yeah. And he received many awards and honors, okay, including the JSPS award and also the Inouye, okay, I maybe pronounced incorrectly, okay, the award, and also the Best Paper Award from the JSPS. And last year, okay, he received the Meson Prize, okay, Meson Award, okay, together with Asuda and Ishii, okay. So the award was given for his work on nuclear force, okay, from Lattice QCD, okay. And this is exactly today's talk title, nuclear force from Quarks and gluons, okay. So let's welcome Professor Aoki.
Thank you very much for the introduction, and it's my great pleasure and honor to give a talk at this colloquium. And today I talk about nuclear forces from quarks and gluons, and maybe let me explain some background and introduction or motivation for this research. So first, I'd like to explain what is a nuclear forces. You may know, but I'd like to emphasize the importance of the nuclear forces in physics. So as you know, we know that there is an atom. Atom consists of the nuclei and also electrons. The electron has negatively charged and found in the 19th centuries, and also the atom nuclei has a positively charged. And people now then realize the nucleus is made of protons, which is positively charged, and neutrons, which is neutral. That you may know that it's have been observed, have been found in the early 20th century, and the neutron has been found in 1932. This is the size of the atoms, and this is the size of the nucleus. And after discovery of the neutron, people wondered what binds this proton and neutron inside of this nucleus. At that time, people only know gravity forces, but gravity forces is too weak, and also people know Coulomb forces. But in this case, it's Coulomb forces opposite. In between protons, it's repulsive, so it's opposite. And also for the neutrons, since it's chargeless, they don't feel any Coulomb force. So at that time, people realized they need some new forces. That we call nuclear forces. And the property of the nuclear forces, one can guess, since it must be stronger than Coulomb forces, because it must produce nucleus against the Coulomb repulsion, and also it must be short range, because in the usual life, people don't see any this kind of forces. So 1935, so just 3 years after discovery of the neutrons, Professor Yukawa proposed some idea called Meson theory. He thinks the nucleons, proton, it's the name of the proton neutrons, interact with each other by exchanging some virtual particles. And because of the short-range interaction, he can guess the mass of this virtual particle because the interaction range is proportional to the inverse of the mass of the particle. And he calculated this mass and found it is heavier than electron but lighter than nucleons. Therefore, it's so mass of the intermediate particles, and then people call it mesons. And nowadays we know that it's so-called pi mesons. And this is a generalization of the electromagnetism. As you know, Coulomb force or electromagnetic forces is intermediated by the exchange of the photon. So electron interchange virtual photons. This produces electromagnetic forces. And similarly, the proton and neutron, or maybe proton exchange pi mesons, and which produces this nuclear force. In the case of the Coulomb, because this photon is massless, they have the potential between electron has 1 over r forces, while because of the mass of the pi mesons, it has some extra factor exponential minus m pi r. Of course, you can see massless limit, it goes to Coulomb force. And we usually like this kind of diagram, the proton-neutron exchange pi meson and interact with each other. We call this kind of diagram the pi meson. So because of this Meson theory, Yukawa got Nobel Prize 1949. This is the first one in Japan. And our institute is founded because of his Nobel Prize. So it's 1953. At that time, our institute is called Research Institute of Fundamental Physics, or RIFP. And therefore, this year, the 60th anniversary of our institute. But 1990, our institute renamed as the Yukawa Institute sorry, not fund, Yukawa Institute for Theoretical Physics. Sorry, mistake. So this is our building. And this nuclear forces, it's very important to understand the structure of the nucleus like this, or also called some strange nucleus called hypernuclear. I will explain this later. And also, this nuclear force is related to the structure of the neutron star. And also, it's related to the supernova explosion. I will discuss this in the next few pages. But after the Yukawa theory, people investigated nuclear force in details and found the more complicated structure like this. This is a modern nuclear forces after Yukawa theory. This is nuclear potential. In terms of the distance r, this is the potential energy as a function of distance between two nucleons. Therefore, the derivative of this potential gives the force. And Yukawa proposed a Meson theory which explains a long-range part of the nuclear potential, this part. So this part is explained by pion exchange, one pion exchange, and which produces attractive forces. But in intermediate range is from 1 to 2 femtometer. Femtometer is 10 to the minus 13 centimeter, 10 to the minus 15 meters. In the meantime, intermediate range, this attraction becomes stronger. And this stronger attraction cannot be explained with one pion exchange alone. And people think it's maybe 2 pion exchange, coherent 2 pion exchange, or heavier Meson exchange like low omega sigma. But more shorter range, like the less than 1 femtometer, this attraction turns into the repulsion. And this repulsion becomes very strong, and people call this is repulsive core. Core is some very hard object inside. And of course, Yukawa theory alone, since it's, you may remember the form. This is 1 over R. If we only have Yukawa force, it diverges alcohol there. But it's oppositely, may not be diverged, but oppositely becomes very positively large at the short distance. So this is modern nuclear force and current knowledge of the nuclear force. And in particular, this repulsive core is very important, or existence of the repulsive core is necessary, for example, for the stability of the matter. Without this repulsive core, nucleus collapse to very dense object. And that means this repulsive core sustains the nucleus as some particular size like this. And as mentioned before, this repulsive core is important for the explosion of the type 2 supernova. Because this type of supernova, first end of the star, because of the gravitational forces, it collapsed to very dense object. But at some point, because of this repulsive core, this collapsion bounds. And this bounds, it starts the explosion. So people think this bounds due to the repulsive core makes the supernova explode. And also, this repulsive core is important to explain maximum mass of the neutron star. Neutron star is, of course, after the supernova explosion, some very small, dense object remains. One of the, sometimes it becomes black hole, but if the particular mass of the star, it becomes so-called neutron stars. And neutron star is very dense and has very large gravitational force, but this gravitational force is balanced to the first is it's made of the almost neutrons. It's fermion. We have the Fermi pressure from the neutrons, and in addition to this repulsive core. And if we don't have the repulsive core, the mass of the neutron star becomes very low because they cannot sustain the heavy neutron stars. And actually, by calculating the size of the neutron star and the mass of the neutron star, we have this kind of, people can have this kind of the graph. If neutron star is very large, mass is very low. It's ratio between neutron star mass and solar mass, so mass of the sun. But if it becomes smaller and smaller, it can have the very heavier mass. And but at some point, it reaches some maximum value. And in the universe, people observe the neutron star, whose mass is 1.5 of the solar mass. And recently, people observe the neutron star with two solar mass, which much heavier than before. And if we don't have the repulsive core, people calculated and found we cannot have such a heavy neutron star. Therefore, the resistance of the repulsive core and the mass of the neutron star is very closely related, and people now think the repulsive core alone can sustain this heavy neutron star or not. And actually, some calculation tells only repulsive core of the nucleon cannot sustain, and we need some extra repulsion, which comes from so-called three-body nuclear forces. I may explain this. So, therefore, the origin of the repulsive core is important. People try to understand what is the origin of the repulsive core. Although there has been many attempts to explain the origin of the repulsive core, for example, the introduction of the omega meson by Professor Nambu. But at this moment, no definite explanation exists because the internal structure of the nucleon becomes very important at such a short distance. As I show, the repulsive core appears at this size of the less than 1 K. So therefore, the understanding the nuclear forces, in particular, this origin of the repulsive core, is one of the most fundamental and solved problem in elementary and nuclear physics. And in this talk, I will explain our effort to answer this question, to mean understand the nuclear forces from the fundamental theory. So this is introduction of my talk. And if you have some questions, please ask during my talk. It's okay. So now I'll go to the second part of my talk. So I will explain why to understand the nuclear forces is difficult. So now I talk about quarks and gluons. Quarks that is the internal structure of the nucleons. You already know, but I would like to explain this. Experimentally, more than few hundred of hadrons are observed. Hadron is the name of the proton, neutron, meson, etc. Therefore, the hadron are not fundamental or elementary parts. And our understanding now is hadron are made of more fundamental objects called quarks. So proton and neutron, which called baryons, which they are made of 3 quarks. So proton is made of 2 so-called up quark and 1 down quark. But neutron is 1 up quark and 2 down quark. And mesons are made of quark and anti-quark. And proton and neutron are made of 2 types of quark, up type and down type. And meson is up type and down type UD quark and their anti-quark. And but in nature we have 6 quark. 1973, Kobayashi and Maska predicted existence of 6 types. This type we call flavors, 6 types of quarks. And so we have up, down. This is more familiar quarks, but we have strange, charm, top, and bottom. There are 6 flavors, and these 3 has a charge 2/3. These 3 have charge minus 1/3 of the electron. And these quarks has some special dynamics called QCD. This is a name of the quantum ChromoDynamics. And QCD is a series of the dynamics of quarks and gluons. Gluon is something like the photons for electromagnetism. A quark interacts by exchanging this gluon. So quark exchange gluon and interact with each other. And the quark has so-called color charge. And in this case, we said it's red, blue, green. There are 3 different charges. And by exchanging these charges, some ability to emit or absorb this gluon. So this is a typical interaction of the QCD. But
I have a question.
Yeah.
About the proposal by Lambu. When was that? Because my understanding was 1973. That was after the asymptotic freedom was discovered. And then Gelman and Neuweiler and some other people. That was a paper, a physical result.
Yeah, okay. So this fact I learned from, I forgot to say some people are going, but this some guy's 16th birthday, Lamb wrote some.
That I understand, but that was not the QCD. That was the he found the quarks and gluons, right?
But the Lamb proposed the quarks also. It's different way of.
But not the fractional.
I think he wrote the non-abelian gauge theory for the in this monogram, I think.
Please excuse my ignorance. This is the first time I see it.
No, I forgot the exact reference, but I will let you know the. I think I also learned from some American guy. He claimed the QCD is invented by Lamb. Okay. So and particularity of the QCD is this gluon itself interact with themselves. So they have self-interaction, like these 3-point interaction and 4-point interaction. Therefore, we have this kind of gluon-gluon interaction. Scattering. So there are two particular properties of the QCD. One is of asymptotic freedom. Forces becomes weaker at shorter distance. That is asymptotic freedom. And this property is demonstrated by these three people, and they got Nobel Prize 2004 by showing this asymptotic freedom in QCD. In general, non-abelian gauge theory. And this is the property of short distance. However, at longer distance, property is very different. It's so-called co-confinement. That is, force of the QCD becomes very strong at longer distance. And therefore, due to this strong interaction, no isolated quark can be observed in this. So this is a picture of for example, the nucleons. Quark bind together with gluon like the spring. Gluon is like spring. Therefore, its shorter distance force is very, maybe not spring, maybe string is better, but shorter distance, there is almost no quark, but no forces. But if you try to separate two quarks, force becomes very strong due to this spring or string. Then, so now our task is, since we know the theory of quark and gluons, and the nucleus is made of quarks, then our task is to derive or to calculate the nuclear force from QCD. That is obvious. However, this is not so easy. So this is a simple Yukawa theory, like pi Meson QCD. But in terms of QCD, we have 3 quarks for protons, 3 quarks for neutrons, and they exchange gluon a lot of, and sometimes the pion exchange. But we have more and more diagrams, and very complicated diagrams have to be calculated. And Lamb said, even now, it is impossible to completely describe nuclear forces beginning with fundamental equation. But since we know that nucleons themselves are not elementary, this is likely asking if one can exactly deduce the characteristic of a very complex molecules starting from Schrödinger equation, a practically impossible task. So Lamb thought it's impossible. In that sense, we have to challenge his statement. And the problem of dealing with this kind of QCD is as follows. Because of the confinement, as I said, force in QCD is very, very, very strong. In this case, we cannot use perturbation theory based on the weak coupling. So we can't use this usual perturbation theory. Therefore, we have to deal with this strong coupling problem. Luckily, we have some method to deal with this problem, so-called Lattice QCD. This Lattice QCD is the following theory. Usually, we consider space-time as continuous. But we approximate this continuous space-time by discrete space-time we call lattice. And we define QCD on this discrete space-time on the lattice. This is the lattice QCD. So we have the discrete space-time point, and this is we call lattice spacing. This is A, and this is the box size A. Good things of the lattice QCD is it's equivalent to the well-defined statistical system if A is non-zero and L is not infinity. And also, this is a little bit technically difficult. It's so-called manifestly gauge invariant, and also it's fully non-parallel. And for lattice QCD, we can use some numerical method, so-called Monte-Carlo simulation technique. So let me explain the lattice QCD in more details. This is two-dimensional shape of the lattice. In reality, we have 4 dimensions, but for simplicity, we consider 2 dimensions. So we have lattice point x and x plus mu. And the cork lives on this discrete point. So cork here, or maybe anti-cork here, or cork here, anti-cork here. But in this line, we call this is link. We put gluons on this link. But by putting gluon a little bit strange form. So this A is corresponding to gluon. But this, we put so-called some link variable u, which made of gluon field in the exponential form. So by expanding, this contains many gluon fields, 0, 1, 2, 3, etc. That means this U contains infinitely number of gluon fields. In that sense, it's non-perturbative. I mean, there are many gluons in this variable, one variable. And actually, as I said, cork has 3 colors. This U becomes mathematically SU3 matrix in this. By calculating some average, we usually use so-called path integral formulation. So let me explain this formula. We have some physical observable O, which made of cork and anti-cork and gauge field U. And we calculate this integral, so integral over cork and anti-cork and gauge field with some weight. So weight depending on gauge field and weight depending on cork. And cork has some bilinear form with very large sparse matrix D, which depend on gauge field. A little bit technical form. But since cork term has very simple form, we can integrate this part by hand. By integrating this cork field, this part becomes determinant of D. And we have some weight for U. Therefore, our task is calculate some quantity which depend on U with this weight probability of U, which made of determinant of du and some exponential factor of Sg. We call this Sg is action of the gauge. And of course, it's almost impossible to calculate this integral because the U lived on all space-time link. So since it's 4 dimensional, it's very complicated integral. However, by using so-called important sampling method according to this probability weight, we can calculate this, we can approximate this integral by some numerical technique, so-called Monte-Carlo simulation. And by using this, we can calculate the complicated QCD process by using supercomputer. But still, even using supercomputer, calculation is not so easy. And I'll explain the recent progress